So, good afternoon all. So, we'll be continuing with the week 11 problem solving section. So, in Monday's class, we had covered almost we had started with the concept of the stochastic hydrology, and we were solving questions related to the basic basic probability and statistics. So, we already had covered what are the different, like we started with the uh, basic statistics, that is how the two branches, that is the descriptive statistics and the inferential statistics. So we started with the descriptive statistics, and we saw how we can uh, what we say we can describe a data set. If you have a particular sample, how we can describe the data set with the help of the measure of central tendency, measure of variance, or measure of spread, or with the measure of symmetry, or with the measure of wickedness. So this is what we saw in the previous class, and also we were solving questions related to the basic theory, basic probability theory, and also we had covered till we had been introduced. We have seen problems related to PMF and PDF. That is, PMF is stands for discrete. That is the probability mass function, which are related to the probability of a discrete random variable. And we saw what is a PMF, which stands for probability, PDF, which stands for probability distribution function, which are defined for continuous random variables. We also saw what is a random variable and what are the different types, that is discrete random variables. The difference also, we saw what is a discrete random variable and what is a continuous random variable. And within discrete random variables, we saw the examples of number of rainfall days, number of thunderstorm days. These are discrete values. And for continuous random variable, we saw problems relate random variables. For example, the maximum annual rainfall or maximum annual discharge. So these are the examples of continuous random variables. And we had almost covered how to find the mean variance related to PMF, and also how we can find the mean variance mode, or even the skewness, kurtosis, and these variance for the if we are given with the PDF also. So next we were coming to the frequency analysis. We had before we go to the frequency analysis, we have been left with the different types of probability distributions, right? So we gave an introduction of PMF and PDF. So then we were dealing with some user defined or predefined PDF and PDFs and PMFs. But there are some standard uh, theoretical PMFs and PDFs that we'll be extensively using in the field of hydrology. So that all we'll be giving an introduction of those in this particular lecture, and we will be seeing both the case of the probability mass functions like binomial distribution, Poisson distribution, etc. And also for the continuous case, we'll be seeing normal distribution, exponential distribution, for the extreme value distributions like Gumbel distribution. So these all will be seeing in this lecture. And also we will be going towards the frequency analysis, which is very much important for design for in the field of hydrology when we are trying to design a hydraulic structure or something. Then the concept of this frequency analysis, return period, risk, these all comes into picture. So that all will be covering in the second part of our week 11 lecture. Before we start, I will give a brief introduction of myself. I am Akhil. I am currently doing my PhD in IIT Delhi. I had completed my BTech from NIT Calicut in the field of civil engineering. Then I did my master's from IIT Guwahati in water resources engineering and management under the supervision of Professor Srija Pekar. And currently I'm working under Professor Dhenya and have enrolled for PhD in IIT Delhi from the year 2022. So straight away we can start. So just like a recap. So we saw what is a random variable, right? So from random variable, there are two types of random variable. That is one is discrete random variable, and the other type is the continuous random variable. Right. And for the discrete random variable, the probability distribution corresponding to those, we call it as PMF, or it is called probability mass function. And for continuous random variables, the probability distribution corresponding to that, we call it as PDF, or probability density function. Right. So we saw some examples of PDFs and PMS. So they were some user-defined functions that were given, and now we'll be seeing some standard or theoretically defined distributions, which will be extensively used in hydrology. So we'll be focusing on those distributions which will be used in the field of hydrology. In that means, uh, which can fit like our in hydrology, our variables are rainfall, discharges, temperature. So these are the hydrological variables, right? So these variable distributions can be fitted using those some particular types of theoretical distribution. Those distribution will be more focusing. Okay, so we can start with the first question. So we had already solved 10 questions from this particular uh, concept of stochastic hydrology. Now we'll be continuing that. We'll be following with our 11th question, that is, for an average occurrence of, find the average occurrence of a 10-year flood. So there is a 10-year flood. What is a 10-year? That you already know, right? 10-year flood means a return period of that flood is 10 years. If you want to be more clear, like if I'm calling it something as a 10-year flood, or if I call this as a T-year flood, this T stands for the return period. Say, if we are defining this particular flood with a condition that probability, exceedance probability, you know what is exceedance probability. So that is another thing that you need to understand. There is something called exceedance probability. So the exceedance probability is nothing but the probability that we define a threshold. What is the probability that that particular threshold can be exceeded? That is called exceedance probability. That is is P of X is greater than or equal to some threshold, capital X. Right. So this capital X is a threshold that we define. Right. So if what is the probability that this particular threshold will be exceeded? And if we are trying to define the flood, if we are trying to say one particular year as a flood year based on the rainfall, we can either define it based on the rainfall it received, or else we can define it using the discharge or runoff the district which it has received in a particular year. And if we are saying it is above X amount, then they are saying there is for this probability, for this particular probability has a return period of 10. That is return period means it is the time of occurrence after every 10 years, or that particular flood intensity, that particular intensity of rainfall, that particular amount of rainfall, that particular amount of discharge can happen once in 10 years. That is the meaning of a return period. It will return after 10 years. In a period of 10 years, it can occur only once. Once it occurs, it can has a chance of occurring only after the completion of another 10 years. That is what a return period means. So that means the chance of occurrence is once in a 10 years. So this probability we can write it as 1 by t. This exceedance probability is the inverse of the return period. So a flood having a return period 10 means the chance of occurrence is once in 10 years. So the probability of occurrence is 1 by 10, right? So the exceedance probability, the probability that the variable that defines the flood exceeds the threshold is 1 by 10 or 1 by t. Okay, so that concept is clear. That is the concept of return period. Return period is the recurrence interval that is after that much year, t years, it will repeat. So a flood having higher return period will be having larger magnitude, right? So if it is a 50-year return period flood, then the magnitude will be very high. It has a chance of occurrence, the rarest events. Chances of occurrence after 50 years only. A 10-year will be having slightly lesser magnitude, right? So it has a better chance of occurrence than a 10-year flood, right? So that is how that is the relation between a return period and the exceedance probability. Okay, I hope that is clear. Then we can move further to the question. Uh, so the question is, we need to find the average occurrence of a 10-year flood in a period of 100 years. So a 10-year flood, you already know, it has a chance of occurrence of once in 10 years. Now we have a 100-year period, then we have to find the average occurrence in this particular period. The probability that exact this the probability that exactly this number of 10-year flood will occur in, so this is the second part. What is the probability that exactly this number of 10-year floods will occur in 100 years? Okay, so these are the two parts of the question. So we need to find the average occurrence and then the probability that the this number, that is the average occurrence of 10 year, will occur in 100 years. That probability also we need to find. Okay, so one thing we can straight away write. So what we just discussed here, the probability, this is what we know from the concept of return period. That is the probability of occurrence of 10-year flood in any year. That would be 1 by t. That is what we just discussed, right? That is 1 by t, the concept of return period. That is point 0.1, right? So this is point 0.1, right? So therefore, now we need to say what is the average occurrence in 100 years, right? So the probability, so the average, so what we need to find is the average number of occurrence in 100 years. So in 1 year, the occurrence is zero point 0.1. Probability is zero point 0.1, right? So if so, 1 year probability is zero point 0.1, right? So for 100 years, we have to say the average number means we have to say the expectation of x, right? That is the average that we saw in the previous lecture. The expectation will be given by n into p, np, n times probability, right? So probability n is 100 years and the probability is zero point 0.1. So it will be 10. Right. So the answer of first question. So it is also, in a way, it is also, we can directly see in the question, we can answer this, right? Because the question is the return period of the flood is 10. So once it will occur in 10 years. So in a 100-year period, there are 10 year periods are there, right? So in each 10-year period, it will occur once. The total number of times, the average number of times of occurrence will be 10. Otherwise, you can find it in this way also. The average is given by the expectation of x, the probability is zero point 0.1, and n is 100, right? So if it was 1000 years, it will be 1000 into p, it will be 100 times. If it was 50, then 50 into zero point 0.1, it will be 5 times. Okay, so that's also the first part of the question. There is one more part. Is what is the probability that exactly this number of 10-year flood will occur in 100-year period, right? So next is the probability of 10 occurrences of 10-year flood in 100 years. So this is what is asked, right? The probability of 10 occurrence of 10-year flood in 100 years. This is what is that is being asked in the second question. That number means that we already calculated as 10. The probability of occurrence of 10 occurrences of 10-year flood in 100 years. So this we can use a theoretical distribution, that is for a discrete random variable. That is number of occurrences is a discrete random variable, right? So that is called a binomial distribution. So we can see what's a binomial distribution. So if you have seen the lecture, this should be very clear. We can make the number of occurrences and all we can model using the binomial distribution. It is defined as p x x x and has two parameters n and p. That is n is nothing but the total number of occurrences and p is the success probability. Then it is given by ncx, sorry, ncx, p raised to x, 1 minus p raised to n minus x. Okay, so this is what a binomial distribution is. Okay, so binomial distribution is has two parameters, n and p. N is the total number of occurrences, and p is total number of occurrences, total maximum number of occurrences possible, and p is the success probability. So here, in this case, if to get the above probability, so we have our x is total number of occurrences that we want is 10, right? And maximum number of occurrences n will be that is 100 years, right? And the success probability is 0.1 that we already found. So we can substitute this to get the probability of 10 occurrences of a 10-year flood in 100 years. So this will be, we can write it as P X X N is 100. So we can substitute for X also. So X also we know we want for 10 years, right? 10 times, not 10 years, 10 times. So 10 times it should occur in 100 years with a success rate or success probability of 0.1. So this is what we need to find. Then it will be 100 C 10, okay, zero point 0.1 raised to 10, 1 minus 0.1, 1 minus P raised to 100 minus 10. So you can solve this using a calculator. So NC10 is nothing but n factorial by r factorial into n minus r, that is 90 factorial, right, into 0.1 raised to 10 into 0.9 raised to 90. So you can solve this using a calculator, and the final answer will be coming around 1.1319. So this is the probability of having 10 number of 10 occurrences of 10-year flood in a 100-year period. Okay, so occurrence of one flood in 10-year period will be one, right? So the return period is one. Uh, it is zero point 0.1, right? So return period is one. So it is return period is 10. That is 1 by 10 is 0.1. So in 10, if you are given with a longer period, 10-year period, and we are asked the this much number it will occur, then we can go for the binodal distribution, which models this particular number of occurrences, right? So I hope this is clear. So in binomial distribution, only thing you have to remember, it has two parameters. That is, it can be used to model the number of occurrences in n years. If we are asked with questions similar to like how much time it will occur in this much period with a success probability this much, then we can directly go for binomial distribution. So where n is the maximum number of occurrences for the, like here it is 100, and x is the occurrence that we need to find. So for 10 years we need 10 times it occurs, right? And p is nothing but the success probability, that is equal to 1 by time, return period is 0.1. Okay, so now we can move on to the next question. So a hydrologist has two possible proposals to consider for the construction of an embankment. So basically an hydrologist is constructing a embankment and he has two possible proposals. So he is having two possible proposals. The details of the two proposals are given as follows. So there are two proposals and the details of these proposals are as given as below. Which proposal should be considered for an economic design? So they are asking which of this proposal we need to consider for an economic design, right? So the economic design means whether we should go for a 5 year, if we are going for a 5 year return period, flood and designing in that way, whether that is economical, or we should go for a 10-year proposal. So we have given with the return period. First proposal as a 5 year return period proposal. Second is a 10-year return period proposal. And the 5 year return period flood is magnitude is 1,400 meter cube per second. So the flood is defined using the discharge, and the discharge is 1,400 meter cube per second. And for the proposal one, and for the proposal two is 2,200 meter cube per second. Time period of occurrence of the event once says that the time period of occurrence of the event once such that once in 8 year and once in 15 year facilities have can be repaired with the revenue earned without any loss. Okay, so that is time period of occurrence of the information we are having is time period of occurrence of the event once says that facility can be repaired with the revenue earned without any loss. So without any loss, so there will be some revenue we'll be gaining due to these particular embankments. So from that revenue we earn. So once in 8 years we can repair the proposal one, right? And in once in 15 years only 15 years of revenue we need to repair for the proposal two, and the proposal one needs only 8 years of revenue required. So which one? So based on this, we have to say which is an economic design or not. Okay, so there is no need of any additional fund. With the revenue generated, we can go for a repair once in 8 years of the proposal one, and once in 15 years for the proposal two. Okay, so we can, for if you understand this question clearly, then we can directly start with the defining our random variable. Okay, the first thing we used to do in any of the question above also we did what we did was we first define the random variable. Okay, so here also we can define our random variable. Let x be the number of occurrence of flood. So here we are defining our random variable as the number of occurrence of flood. Okay, so the number of occurrence of the flood is defined as the random variable here. Okay, so we can start with the proposal one. Okay, so in proposal one, if the flood is given a flood of the given magnitude, so the given magnitude of flood he is 1400. Okay, given magnitude occurs once and does not occur at all, then then there will be no loss, right? So, so if the flood of the given magnitude occur once or does not occur at all, so then there will be no loss, right? So they actually in this question they have said if it occurs once, and once means in once in 5 years it will occur, right? Then because in the eighth year we can go for a repair. So that is fine. And if it does not occur at all, then then also there is no loss, right? Once it can occur, there is no loss. Does not occur at all, then also there is no loss, right? So we can mention that. So, so one thing we can understand from the proposal is that if the flood of given magnitude occurs once. Either it can occur once or does not occur at all. Then there will be no loss. Right. So if the flood of the given magnitude occurs once or does not occur at all, then there will be no loss because we have our revenue to back up those one particular occurrence. So So x can take either value 0 or 1. It can occur 0 times or it can occur 1 time, right? So x can be 0 or 1. So now if you understood the Bernoulli here, so it is similar to a Bernoulli process, right? It is the how much time can occur within this period, right? So So it can occur either 0 or once, right? So it is similar to a Bernoulli process. Now this is a Bernoulli process, and we have our so we can model this as a Bernoulli process. So this is a Bernoulli process. So we can use a Bernoulli distribution. So we will be making use of the Bernoulli distribution. So to define Bernoulli distribution, we need two things. That is, what is n we need to find, and what is p, and what is x. These three things, if you know, we can apply the Bernoulli distribution, right? So here, p we know the success probability. That is, the flood will occur. The probability of occurrence of flood is inverse of return period, right? So 1 by T1, so that is equal to 1 by 5, right? 1 by 5 is 0.2. And N, what is N here? So N here is 8, right? So, so here, if there shouldn't be any loss, if there shouldn't be any loss, it can occur in without any loss. If we have to maintain in 18 years, it should in 8 years it should occur at least once, or it should not at all occur, right? The maximum number of years that we consider here is 8 years, because after beyond 8 years we cannot keep the threshold, because beyond 8 years, within once in 8 years we can minimum 8 years, minimum 8 years is required to get the revenue to repair it, right? So n is equal to 8, n will be equal to 8, and so let's say we move it down. So n will be equal to 8, and what is left is x. X is equal to 0 and 1, that we already know. So it should not occur, and or it should can occur once. So these are the two possibilities of x, that is 0 or 1, right? So that particular probability is P of x equal to 0 and 1. You can write the parameters also here. Uh, so we can write Pf x. The required probability is of x. Parameters are 8 and zero point 0.2. That is NNP plus P of x. X is equal to 1 with the parameters 8 and 0.2. Right. So this we can write it as 8C0 into zero point 0.2 raised to 0, 0.8 raised to 8 plus 8C1, zero point 0.2 raised to 1, and zero point 0.8 raised to 7, right? So this is direct application. Then if you could solve, 8C1 is 8, and this will be 8 into 1 into zero point 0.8 raised to 8 plus 8 into zero point 0.2 into zero point 0.8 raised to 7. So this will be 0.168 plus 0.335. So if you add this, it will be coming around 0.503. So this is the probability of occurrence of flood without any damage, without any probability of occurrence of flood without any damage or without any loss for the proposal one, that is equal to 0.508. Okay, so now so this is the probability, right? So the probability without any loss, the probability is this. So the probability of loss. So therefore, probability. So no loss probability is this much. Probability of loss will be 1 minus P of P, that is equal to 1 minus 0.503, right? So that will be around that will be around 0.497. Okay, just a minute. Okay, so the probability of losses for the proposal one is 0.497. Now we need can look into the probability of loss for proposal two. So proposal two. So here also what we can do, we will be applying the same. We will consider the Bernoulli process. So we can see the parameters. So P will be probability will be the return period is 10. The probability is 1 by 10, that is equal to 0.1. N is same. N is here, N is not same. Repair is done in 15 years once, right? So 15 is N, and what all is X can X is same 1 and 0, 0 and 1. Right. So here also we can say Px x equal to 0, 15 0.1 plus Px x is equal to 1, 15 and 0.1. So that will be 15 z0, 0.1 raised to 0 and 0.9 raised to 15 plus 15 c1, 0.1 raised to 1, 0.9 raised to 40. So this, if you solve, it will be around 0.260, and this will be around 0.343, and total it will be on 0.5949. So 549. Okay, right. So here also then we can find the loss probability. So the loss probability is equal to 1 minus 0.549, that will be 0.451. So the loss probability is more if you compare it is more if you compare these two probabilities, 0.497 and 0.4451. So the loss probability is more, just a minute. The loss probability is more for the proposal one, right? Proposal 2 is having a lower loss probability. The second proposal, the probability low is lower than first proposal, so the second proposal is more economical, right? So we can say the the loss probability of proposal 1 is smaller than proposal 2. So that is no, that is not. So more economical proposal is proposal 1. Okay, that is how we computed the loss probability for the both the proposals, and then we came up with this. We found that proposal 1 is having a lower loss probability, and then we say the more economical one is proposal 1. Okay, so the thing is that we have to define the random variable, and then we need to come up with the possibility that here the x can take only two options, that is it can take 0 1, because in the return in the period it can occur only once in 8 years, right? So once in 8 years if it occurs, then there won't be any loss, and also if it doesn't occur in 8 years also there is no loss in proposal 1. And in proposal 2, if it occurs once in 15 years there is no loss, and also if it doesn't occurs, then also there is no loss, right? So that is how we calculated, we kept the n value, and the possibility of occurrence is once. If it was said, if it occurs twice in 8 years, there is no issue, right? Then we could have taken, in this case, the probability of x equal to 2 also. Right. And in the proposal too, if it was mentioned, if twice in 15 years, if it occurs, it can be covered by the revenue generated. Then also we needed, along with this, we need to add the probability of x equal to 2 also. Okay. That is how we tackle this similar questions. Okay, so both the questions we have tried to fit Bernoulli's distribution. So I hope the Bernoulli distribution is clear to you, and also the questions related to the number of occurrences, the average number of occurrences. Average of number of occurrences in n years if the success rate is this much. So in such cases, we can always go for Bernoulli distribution. So now we can move on to the 12th question. That is, what is the probability that flood with a return period of 10 years will occur in 4 years? So this is similar to what we already did, right? So here, what we'll be doing, we can solve this with using two tip- two types of distribution. We already saw how to solve this similar question using Bernoulli distribution, Bernoulli or binomial distribution, right? So Bernoulli, but it is a Bernoulli process. We will be using this distribution is called binomial distribution, not Bernoulli distribution. The process is called Bernoulli process, and this distribution is called binomial distribution. Okay, so here also we had used binomial distribution. Okay, so the process is called Bernoulli process. Okay, and so in this case we can use two distributions. So one is binomial, and also we can try this with Poisson distribution. Okay, so these two distributions can be used in general for similar number of occurrences in this much times in this much years. That in such questions we can use both the distributions. So we'll first see the case of Bernoulli distribution, the binomial distribution. Okay, so here uh, the return period is 10, right? So our P will be 1 by 10, that is equal to 0.1, and uh, N will be 4 years, right? In once in 4 years, and X will be 1. Okay, once in 4 years, X will be 1. So which is next is a substitution. So P X and it is 1 parameters are 4 comma 0.1. That will be uh, so this will be 4c1, right? P raised to x and 1 minus p raised to n minus x, that is 4 minus 1 3. So this will be coming around 0.292. So this you already know. So we just have to find the parameters. P is the return period, 1 by x is probability 1 by return period, and n is the total number of occurrences. So here it is set once in 4 years. In 4 years, 4 times it can occur, right? So maximum number is 4, and x is the occurrence that we need to find. So once in 4 years they are set. So x is equal to 1. So there is direct substitution. Now we can try with Poisson distribution. So with Poisson distribution, so Poisson distribution, it has only one parameter. Okay. So the parameter, there is only one parameter and it is defined x. Uh, so in general, we define it in this way. X lambda is the only parameter and it is defined by x e raised to minus lambda by x factorial, where x is equal to 0, 1, 2 discrete values till some value n. Okay, so this is our Poisson distribution. It has only one parameter lambda. And how we can find this one parameter, this particular parameter lambda? That is the question. So if we know lambda, we can directly substitute because x already we know for which particular x we need to find. So coming to Poisson distribution, we need to find the parameter lambda. So I'm trying to define the parameter here. So the parameter lambda, so lambda, we can say is the expected number of 10-year flood, that is having a p equal to 0.1, right? 1 by 10 in 4 years. That is the expected number or the average number. That is n equal to 4 years. That is called lambda. So that expected number, that is expectation of x, that is we can find using NP formula, right? So that is n is 4 and p is zero point 0.1, that is equal to 0.4. So our lambda is nothing but the expected number of 10-year return period flood in 4 years. That average number is defines the average number of expected value defines uh, the average number. Just a minute. Right. So lambda is nothing but the expected number or average number of occurrences in that particular period. Okay, that we can find using NP. So x lambda is equal to NP. So if we know lambda, then we can directly find P, find the probability, required probability. So of one occurrence in n years, we can find it as x equal to 1 will be lambda e raised to minus lambda by x factorial, that is equal to 0.4 e raised to minus 0.4 by 1 factorial is equal to 0.268. So if you compare these two values, so these both are the probability of occurrence of one flood in 4 years. One flight means one 10-year flight in 4 years. 10-year return period flight in 4 years. Once in 4 years. So both are coming approximately same. One is around 0.292, one is 0.268. Okay, so it's a matter of how which distribution which we assume that our data will follow. So we assume that our data, that is the occurrence of flood, will follow a binomial distribution. With that assumption, we will be coming to a probability of 0.292. If you assume that no, our distribution of a number of occurrences that will follow a Poisson distribution, then it's coming around 0.268. So both are almost the same only, right? So this is the two distributions that you can, discrete distributions that you can be using whenever we are dealing with the case where we are dealing with the case of n occurrences, that is n occurrences, x occurrences in n years with a success rate of p. Okay, now we can move on to the next question. Uh, that is, what is the probability of fewer than two occurrences of a storm in a 50 year? What is the probability of fewer occurrences of fewer than two? That is less than two occurrences of 10-year flood. So here, uh, which distribution you want to use? We have already done two questions related to Bernoulli, right? Now we can go for we can fix that this will follow a Poisson distribution. So I'm saying X follows Poisson distribution, and X is nothing but number of occurrences of storm or the 10-year storm. So that is X. Okay, so with these two assumptions, first thing we need to find is lambda, right? So here lambda, so that you already know lambda how we used to find. We used to find lambda. Lambda is nothing but given by NP. It is the average number of occurrence, right? N into P. So here the question is two occurrences in a year of, so N is here is 50. So N is 50. So here the N is 50. Total number of years is 50, and our return period is 10. So P will be 1 by 10, that is 0.1. This will be 0.1 into 50, that is equal to 5. So 5. So 5 is the average occurrence, right? 5 is the average number of occurrence of this particular flood. Average 5 times it occurs in the 50-year period, right? So we got lambda. Now we can say the probability of fewer than two occurrences of 10-year storm in a 50-year period. So this is what we need to find, right? So this can be written as P of number of occurrences less than 2. That we can say that is probability of X less than or equal to 1. That is P of X equal to 0 plus P of X equal to 1. So if you could substitute it in the Poisson distribution equation, then it will be summation of, so only the summation, we just have to add two terms, right? It will be X, so the equation would be, so I can write it somewhere here, P X lambda is equal to lambda raised to x e raised to minus lambda by x factorial. So this is the equation that we need to substitute. So it will be x equal to 0 will be lambda is 5, 5 raised to 0 e raised to minus 5 divided by 0 factorial plus 5 raised to 1 e raised to minus 5 1 factorial. So this will be adding up to 0.04. This is the probability of fewer than two occurrences of a 10-year storm in the period of 15 years, 50 years. Okay, so we can use both either Bernoulli or binomial distribution, or we can go for Poisson distribution. Same question we could have done with the binomial distribution also. Okay, so we can start with the 15th question. So consider a mean daily temperature at a location to follow a normal distribution. So this is related to a normal distribution. So normal distribution uh, with a mean uh, with mean 10 with mean of 10 degrees Celsius and a standard deviation of 5 degrees Celsius. So we have to use a normal distribution, and it has two parameters, mean and variance, that is equal to 5 and standard deviation is 10 degrees Celsius. Okay, so first we need to know what is a normal distribution. So basically we are now going to deal with uh, PDFs, that is probability density functions that are defined for continuous variables. Okay, so first of all, I will write what is a normal distribution. So normal distribution is, so we define PDF using f of x is defined by 1 by sigma root 2 pi, okay, e raised to minus 1 by 2 into x minus mu by sigma the whole square. So f can be from minus infinity x to plus infinity. So this is how we define a normal distribution. This seems to be a complicated equation. It has two parameters. The parameters are, so this is a normal distribution, and the parameters are the mean and the standard deviation, mu and sigma. The two parametric distribution is a continuous distribution defined from minus infinity to plus infinity, and this is the PDF. And if you look, and its ranges will be, so the plot, if you could see, it's like a benign, it is a bell-shaped curve. Maximum, it will be, probability will be at the mean, and it will be decreasing tails to the extreme values. It's a bell-shaped curve. And this is our x, and this is our f of x, or our PDF. Okay, So this is what a normal distribution looks like. So being a complicated equation, we need to solve this for each of the x values. No, so that's why we have something called standard normal distribution. So the standard normal distribution equation, what we are basically doing is that we assume a standard normal variate, a new variate that is variable z that is equal to x minus mu by sigma. So you can see within this particular term, there is a term for x minus mu by sigma. We are assuming that our uh, x minus mu by sigma is equal to this thing, right? And we will be using this to define our standard normal distribution. We can define it as, if I could, g of x or g of x as 1 by root 2 pi, okay, and e raised to minus x square by 2. So this is the formula for a standard normal distribution. So the advantage of the advantage of this is that when we do this, then our mean mu will be equal to become 0 and the standard deviation sigma will be equal to 1, right? So what the advantage is that this particular bell-shaped curve, particular bell-shaped curve was can be defined only can be defined for the shape of the curve will vary with when we say for different mean and different variance, right? So this location will be for mu. Sorry, this location will be mu, right? So based on the change in mu, the distribution is symmetric to mu, right? So bell-shaped curve, this is will be symmetric with respect to mu. So with the changing values of mu, this will also change. So instead, if you convert this to a standard normal distribution, if you convert it to a standard normal variate, then the advantage is that the it will be symmetric about 0. So this is our standard normal variate and it is symmetric to our 0 and the shape will be also here also it will be a bell-shaped curve. And for this particular curve, for different uh, z value, this is a standard curve and there are standard tables are available. It is g of x. So this curve values we can take from standard set tables. Okay, so there are standard tables are available to get these curves. So it's a table from standard is a tables. We can get these values. Okay, so now we can come back to the question. So the question is consider a consider a mean daily temperature at a location to follow a normal distribution. So we saw what is a normal distribution, how we can uh, reduce it to a standard normal distribution, and how we can get the values of probability using a standard normal distribution tables which are already available. Okay, So for that, for each value of z, we the values of probability are defined. Okay. So they have mentioned the parameter as 10 degrees Celsius, mean is 10 degree, mu is 10 degree, and standard deviation is 5 degree. What is the probability that the mean daily temperature is between 15 and 24? Okay, so we can start with the A part. So they have mentioned probability of 15 and between 15, temperature between 15 and 24, right? So what we can do is first we need to convert this to standard normal variates. So Z is defined as x minus mu by sigma. So here mu is given by 10. The question that is given, mu is 10 and sigma is 5. Sigma is 5, right? So Z corresponding to 15 is, so we can write 15 minus 10 by 5 less than or equal to x minus mu by sigma less than or equal to 24 minus 10 by 5. So this will be P of uh, so this will be nothing but P of 1, 1 by 1, 1 less than or equal to this. We can call it as Z, standard normal variate, and this will be less than or equal to 2.8, right? So this is probability that, so if I could draw the standard normal table, so this will be 0, it is symmetric to 0, the standard normal table. So it is a probability of if for z equal to 1, this is z equal to 1, and this is equal to 2.8. So this particular probability, this particular shaded region, right? So this I can write it like in this way also. So this will be equal to f cumulative probability at x equal to 1, uh, x equal to 2.8, sorry, x is equal to 2.8 minus cumulative probability of x equal to 1. So this means what I'm doing, so for the cumulative probability of x equal to 2.8 is this particular region which I have shaded. And if I'm subtracting that with cumulative distribution of x is equal to 2.8, that will be this particular region. X equal to 1 will be this particular. So whatever is left is the yellow shaded region, right? This is something that will be left, right? So in this way we can find, so we need to find the cumulative distribution from the standard normal tables from this. Okay, so I can uh, show you how we can come up with standard normal tables. So if we search standard normal distribution tables, so there will be a number of tables, so you can take any one. So I can copy this particular table. So it has only values till 1. If I could have a complete table, that would be better. So we can take this, right? So we have this particular, we can copy this. So we can see whether we can paste it here. No, it's not visible, so we can Look for a better one. Hmm, this looks fine. Sorry. Can paste this here. Just not copied. Okay, so we can directly get the value of z is f z is equal to 2.8 and f z is equal to 1, right? So this we can directly get from any of this table. So if this is visible here, uh, this doesn't has value still 2.8. So I can take this particular table also. So permits, if I could paste it here. Okay, so 2 has been inserted and delete this. Okay, so from this, I think we can find. Right. So here, the so this is how a standard normal table looks like. So it has a graph showing what probability it is representing. So these are the Z values. So Z less than this particular, it is what it is being showing. So basically, if it is, if we want f of Z, if we having this particular graph with you, and if we want f of Z of 2.8, that is, that corresponds to somewhere here, right? So here it will be 2.8, and we need this particular shaded region is what we require, right? Or else I can draw it out and outwards. So basically what we need is, so this is our standard normal distribution, and so this is our 0, and what we need is 2.8 here and this particular shaded region. And this I can write it as, for this, from this particular table, it will be equal to 1 minus the probability corresponding to p less than 2 point. So no, this no, this will be, so this probability will be, so this shaded region will be same as 1 minus the probability corresponding to x is equal to minus 2.8, right? So if x is, this is symmetric, so this will be minus 2.8, and this particular area which I have marked here and this particular area which I marked here are equal, right? So from this I can find the probability of x is equal to minus 2.8. So x is equal to minus 2.8 can be, so here we have 2.8 here, right? So we have 2.8 here, 2.80, right? So it will be 0. So this will be, this I can write it as 1 minus 0.0026, right? Minus f equal to 1 also, same principle I can apply. And 1 minus, for that I have to see f equal to minus 1. So f equal to minus 1, the probability is this much. That is 0.1587, right? So if you could do this, this will be coming out to be, this will be, this will be equal to 0.997 approximately minus 0.841, that equal to 0.156. So that is the probability of our temperature between 5, 15, and 24 degrees Celsius. Okay, so there will be different charts. If you, as you see in here, there can be different types how we define these charts. There are different ways how we define how these standard normal distribution values are defined. Seeing the chart or the graph given below, we can decide how we can read this. Okay, so basically we got it. And for the B, if we can move on to the B part. Okay, so B part of the question is, what is the probability of mean daily temperature is greater than 5 degrees Celsius? So mean daily temperature is greater than, so P of x greater than 5. That we can write it as P of 1 minus P of x less than or equal to 5, right? So that we can write it as 1 minus P of x minus mu by sigma. We have to convert it to standard normal variates, right? It's equal to 5 minus 10 by 5. So that is 1 minus P of x z less than or equal to minus 1, right? So z less than or equal to minus 1, we can directly find, right? We already found it, right? 0.158 is equal to 0.11587, 587. That will be coming around 0.841. That is the probability that the mean daily temperature will be greater than 5. So there is one more question, C part. What is the probability that the mean daily temperature is less than 20 degrees Celsius? So we can, so it's so simple. Only thing we need to know how to see a standard normal distribution. So x less than P of x less than 20 degrees Celsius, right? So that we can write it as P of x minus mu by z less than 20 minus 10 by 5, that is equal to P of z less than or equal to 2. So P of z less than or equal to 2. We can apply the same principle that we applied here when we found it for 2.8, right? So that will be nothing but 1 minus P of z less than or equal to minus 2. So for minus 2, the value is around, if you see minus 2, 0.0228. So 1 minus 0.0228, that is equal to 0.977 approximately. So this is how we use a standard normal table to find these values. Okay, so this is how a standard normal distribution is defined. Then we define this is also defined for minus infinity less than x less than z, z less than infinity, and this is the standard. So here, sorry, so this will be z. So there is a correction. So the variable we can write as the standard normal variable z, right? So here also we can write it as z. Okay, and so from seeing these standard graphs, we can directly solve these questions. Okay, so now we'll be coming to the basically the extreme value distributions. So we can start with the extreme value distributions. So that is a Gumbel distribution. So in a certain stream, the annual maximum discharge follows a Gumbel distribution. The annual maximum discharge follows Gumbel distribution with a mean value. So the mean value is given as 12,000 meter cube per second and standard deviation is 4,000 meter cube per second. What is the probability that the maximum annual discharge exceeds 16,000 meter cube per second? What is the magnitude of maximum annual discharge with the return period of 100? So this is how we need to fit to a Gumbel distribution. So we need to see what is the Gumbel distribution. Once we fit to a Gumbel distribution, we can directly uh, find the probability, right? So basically, it is easier to remember the CDF, that is cumulative distribution function of Gumbel distribution. The CDF of that is capital F of x, so and that is x alpha beta are the what we say the variables is given by minus exponential of exponential of minus exponential of minus x minus beta by alpha. So this is the CDF of a Gumbel distribution. This is how a CDF of Gumbel distribution is defined. So here x can take both positive and negative values minus infinity less than equal to x less than equal to infinity. So this is how we define a Gumbel distribution. The parameters are, there are two parameters. They are alpha and beta, right? And also if we have there is some relation that we can see. So the variance of x is related to alpha by this relation 1.65645 alpha square. If we know the variance of the distribution, we can relate it like this. And if we know the expected value of the mean of the distribution, that is equal to beta plus 0.5772 alpha. So this is something that you need to be knowing about the Gumbel distribution. So Gumbel is basically comes under a extreme value distribution. So these are basically used to fit extreme values like the maximum discharge, which has rare occurrences. Right. For in this case, if you see a normal distribution and all, the tails, that extreme value, the tails will have very small probability of occurrence, right? So it is not a good distribution for modeling extreme values, right? So if you want to model extreme values, we go for distributions like Gumbel distribution, right? Okay, so your question we have given with the mean and variance value. The mean value is, so the mean is expectation of x. Expectation of x is equal to, is given as 1200, no, 12,000, and variance of x is given as 4,000. Okay, so the variance of x, so var of x is equal to 1.645 alpha square. So alpha is equal to square root of 4,000 square divided by 1.645. That will be coming around 3118.7. Okay, just a minute. So we got alpha. Now we can substitute to find beta. So expectation of x is equal to beta plus uh, 0.5772 alpha. Okay, so expectation of x is 12,000 is equal to beta we need to find, sorry, beta we need to find plus 0, sorry, so beta value we need to find, beta value is uh, beta plus 0.5772 into alpha, that is 3118.7. So if you solve this, beta will come around 10199.88. Okay, so we got both alpha and beta, the parameters we know. Now it's we need to substitute it to get the this particular. So the required probability. So what is uh, the question is, the first part of the question is the probability that the maximum annual discharge exceeds 1000, 16,000. So P of X exceeding 16,000, right? This is the question. So this we can write it as 1 minus the cumulative distribution, PF less than or equal to, that is 16,000. So this cumulative distribution equation I've already given to you, right? So we can just substitute. That is 1 minus exponential of minus exponential of minus x is 16,000 minus beta, beta is 10199.88 divided by alpha 3118.7. Okay, so this is the probability, and this, if you solve, it will come around 0.144. This is the required probability there of x. So the probability of exceedance, so the x greater than the stream flow or the discharge greater than 16,000 is 0.144. Okay, and so we can, so there is one more part. Second part is what is the magnitude of annual discharge for the return period of, so the probability is return period is given. So from that we can find the exceedance probability, right? That concept we already saw. So the exceedance probability is equal to 1 by 100. From that we can find what is x. So here the part B, so this is part A. So part B of the question, the return period is given. So the exceedance probability P x greater than some threshold that we need to find is equal to 1 by 100, that is equal to 0.01, right? So P x greater than equal to small x is equal to 1 minus P of x less than or equal to x. Okay, so that is cumulative distribution. This is nothing but 1 minus f of x. So we can write it as 1 minus exponential of minus of x minus alpha beta by alpha. So this will be coming out to be 0.01. Okay, so from this we can solve for x. We can solve for x, and finally it will be coming out to be, to solve it in calculator. It will be coming out to be x is equal to 2454 6 24,000 24,546. Okay, 546 meter cube per second. So this magnitude has a maximum discharge, has a return period of 100. After every 100 years, a discharge of maximum discharge of this will occur, 24,546. Okay, so this is how we use Gumbel to model extreme value distributions, extreme values. Okay, the only thing you have to remember, it's easier to remember the CDF. That's why I've given CDF. We can always convert the required probability into the CDF format, and then we can solve it. Okay, and these relations, how mean and variance is connected to alpha and beta. Okay, so we can move on to the 16th question. Uh, Determine the probability that annual maximum discharge at the river gauging station will be equal or exceed 4,000 at least once in next 5 years. So it's a river gauging station is there. So the maximum discharge will exceed a particular, will be equal to or exceed a particular value, that is 4,000 cubic once in 5 years. Okay, that is what is being asked. Assume the return period of this that particular magnitude is already given. The return period is given to us. We need to say this is similar to a frequency analysis question, right? So you're given with the return period. We need to say that we need to find the probability that the it will exceed it will be exceed once equal to or more than this at least once in 5 years. So we have been given us with the return period. So so the return period is once for the flood is 3.625 years. So the exceedance probability. So we can find the exceedance probability. Exceedance probability of magnitude also we know, right? Is 4,000 cubic. That is equal to 1 by 3.625. That will be around 0.276. So we got the exceedance probability with us. So what that is being asked in the question is, what is the um probability that annual maximum discharge at river gauge station is equal to or greater than this exceedance probability at least once in next 5 years. So it will occur once in next 5 years. So probability that it will occur at least once. So probability it will occur at least, so you can say at least once in next 5 years. So the negation of this will be equal to 1 minus, so we can apply this idea, 1 minus probability that it will not occur in 5 years. All the 5 years it doesn't occur. So that is the negation of this particular probability, right? So 1 minus, so the probability of not non-occurrence is 1 minus p, right? 1 minus p, and it should not occur in the coming 5 years. So raised to 5. That is 1 minus p is 0.276 whole raised to 5. This will be coming around 0.801. Okay, so this is how we know the return period. So we need the probability of occurrence of at least once in 5 years. So it will be opposite of probability of not occurring in the 5 years. So 1 minus that probability, that particular probability will be given by the 1 minus p whole raised to 5. So it will be coming out to be 0.801. So 0.80% chances that it will occur at least once in the next 5 years. Okay, now we can go on to the 17th question. If the return period of a severe hurricane in North America is 243, a hurricane occurs in North America, it has a return period of 243 years, then find out the probability that no such hurricane will occur in next 10 years. This is similar to what we just did, right? So consider the occurrence of severe hurricane to follow a Poisson distribution. So it is mentioned in the question that it will follow a Poisson distribution. So Poisson distribution, we have already seen what is the Poisson distribution. So it has only one parameter. It is a discrete distribution with one parameter. So that particular parameter is nothing but lambda, and lambda is the average occurrences, right? So here lambda is given, we already saw lambda is given by n into p, right? So n into p gives lambda, right? So here n, we need to find what is n and what is p. So the return period is given. The return period is given by t is given by 243 years, and so p will be 1 by t, that is 1 by 243, that will be equal to 0.0041, right? And it, next 10 years, so n will be 10 years. So our lambda will be np, that is equal to 10 into 0.0041, that is equal to 0.041. So this is the return period. Okay, so this is the return. This is the, what we say, our lambda, our parameter lambda. The probability of non-occurrence. So the probability of non-occurrence. So that is x equal to 0 for lambda 10. So that will be equal to, so this is given by p. So if I hope you remember, x lambda is given by lambda raised to x into e raised to minus lambda by x factorial. So lambda is 0.041 raised to 0 to e raised to minus 0.041 divided by 0 factorial, that is 1, it will be coming around 0.96. So 0.96 is the probability that it won't occur, the hurricane won't occur in the next 10 years. So we have used the Poisson distribution, and non-occurrence can be done in this way. Okay. So we can move on to the 18th question. If the exceedance probability of a particular flood is 1 by 50th of its non-exceedance probability. So exceedance probability of a flood is 1 by 50th of its non-exceedance probability. Okay. Then find out its return period. That is the first part of the question. So this relation is given. We need to find the return period. Okay. So it is direct straightforward. So if we say exceedance probability, so exceedance probability, if we take it as P, and non-exceedance probability, if we take it as Q, so P plus Q, that we know it as 1, right? So they are saying the exceed non-exceedance probability. So again, question is given, so it is given that non-exceedance probability Q is 50 times exceedance probability P. So P plus Q equal to 1, that we know, so we know. So P plus 50P will be equal to 1. 51P is equal to 1, and P will be equal to 1 by 51. So 1 by 51 is nothing but 0.0196. So that is our exceedance probability. So they are asked to find they're asking us to find the return period. So return period is nothing but return period is nothing but 1 by P, that is 1 by 0.0196. That will be around 51 years. Okay, that is straightforward. That is the first part. There is one more. Consider the flood. Next part is also find the probability of such event occurring exactly once in 10 successive years. Consider it follows a binomial distribution. Okay, so this also we have solved similar question. So it follows a binomial distribution, right? And also we have our once it's exceeds once in 10 year, right? So n is equal to 10, x is equal to 1, and p we already found it as 0.0196. And the Bernoulli binomial distribution is given by p x x n p is given by n c x p raised to p raised to x q raised to n minus x, where q is equal to 1 minus p. Right. So we can substitute that to find probability of x equal to 1, n is equal to 10, and p is equal to 0.0196. That is 10C1 0.0196 raised to 1, 1 minus 0.0196 raised to 9. So that when you solve, it will come around 0.163. This is the probability of occurring once in next 10 years. Same return period flood occurring once in next 10 years. Okay, So we can move on to the 19th question. Okay. So the mean annual daily rainfall of a city is 105. Mean is given, and the standard deviation is also given. Determine the depth of rainfall with a return period. So return period is given. So we know the exceedance probability from that 1 by 5. Using Gumbel method and assume the sample size is very large. So we assume the sample size is very large, and we need to find the depth corresponding to a 5-year return period. And we need to assume Gumbel's distribution, follows a Gumbel's distribution. Okay, so for this, two things you need to see. So we are given with a sample. So sample has a mean X bar that is equal to 105 mm, and we have S standard deviation as 45 mm. And so in case of Gumbel, so one thing was we know there was a inside the exponential, this term was coming 1 minus beta by alpha, right? So this we can call it as YT. So this is called reduced variate, reduced variate, similar to what we did in the case of normal distribution when we reduced it to a standard normal distribution. So then there is a relation which we have derived of YT with the what we say the return period. YT is equal to minus of ln within bracket ln t by t minus 1. So this is a relation that we uh, derived for the case of a Gumbel distribution. Okay, so if we know this particular distribution, we know return period t is equal to 5. So yt will be reduced variate corresponding to the return period 5 will be ln within ln 5 minus 5 by 5 minus 1. So if you solve this, the reduced variate will be coming around 1.5, right? So as the sample size is very large, is given the question, right? So you can directly use. So there is something called a frequency factor, KT. So frequency factor is related to the reduced variate y as yt minus 0.5772 divided by 1.28. So this we have already seen in the lectures, right, while deriving 2825. So the reduced variate, we can get it for each of the return period, we can get the reduced variate with this particular relation. And once we get the reduced variate, we get the frequency factor or KT, we call it as KT using this expression for a Gumbel distribution. So we already know what is YT. YT is 1.5. So we can just multiply, substitute to get what is our frequency factor KT. That is coming around, if you substitute it, will come around 0.72. Okay. So once this is done, uh, next if we have a KT and YT with you, a KT with you, we can find XT. If we have KT with you, we can find XT as X bar plus KT times the standard deviation. Okay, so these are the things you need to remember from Gumbel distribution. So if for any given t, any given return period, we can find the reduced variate yt. If we have the yt with us, we can find kt using this particular expression. If we have kt, and for that particular kt, we can find our xt using this expression x bar plus kt into s, where x bar is the sample mean and s is the sample standard deviation. So here our xt will be Mean was 105 mm plus KT, we got a 0.72 into standard deviation was 45, right? So this was coming around 137.04 mm. So this magnitude has a return period of 5 by using Gumbel distribution. Okay, so you just need to remember these three relation, how the reduced variate is related to the return period, how the period is reduced variate and frequency factor are related, and if you know the frequency factor and the sample mean and variance, how we can find the new corresponding x value. Okay, so we can move on to the final question. So it is one which I've taken from the plotting point method. So consider an annual flood discharge of this much QMX. So it is given for each year. What is the annual maximum discharge is given. Recorded a river gauging station over a period of 10 years as shown below. So these are the years and this is the maximum discharge. Then we need to, with this data, we need to find the flood magnitude corresponding to 5-year return period, 10-year return period, and 25-year return period. And also we have to find the return period corresponding to 4000 QMX. Right. So how we can do if we are given with the data. So one way to do this is if we are given with the data, we can find the mean variance, we can fit it to a Gumbel distribution or something, and we can do it. Right. So here, if we can get the mean and variance, if the mean and variance, how it is related to alpha and beta, we know, then we can estimate alpha and beta. Then if we have the alpha and beta, we can find the exceedance probability. Then inverse of the exceedance probability will give us uh, the flood magnitudes. Inverse of exceedance probability will give us a return period, right? Similarly, if we are not going to use any of the distribution, how we can solve using this if we have the data with us. That is what we are going to see. Okay, so the thing we will be using plotting point method. So the first thing we need to do is we have a data with us. First, we have to arrange it in the descending order. This data we have to arrange in the descending order, and we will giving ranks. So there are total 10 data. So this column is for the rank. So rank will be from 1 to 10, right? 4, 5, 6, 7, 8, 9, and 10. So there are 10 data and for each. So if you could arrange based on the in the descending order, first highest value is 6,100, 5,020, then 4,700, 4,550, 4,200, 3,780, 3,320, 3,150, 2,890, and 2,500. So these are the values of discharge arranged in the descending order. Then we'll be using different formulas. So here I am using the formula to give the exceedance probability as rank by n plus 1, m by n plus 1. The numerator is a rank and denominator is n plus 1. N is equal to 11, right? So this will be nothing but m by 11, 10. M plus 1 will be 11, right? M by 11. So corresponding the exceedance probability will be, so this will be having the least probability is the rarest. So least accidents probability, then the probability will increase. That is 2 by 11, that is equal to 0.182. This is 3 by 11, that is 273. This is 4 by 11, that is 0.364. Similarly, we can find other values 0.455. This is 0.545, 0.636, 0.727, 0.818 and 0.909. Okay, so we got the exceedance probability. So if we have the exceedance probability, we can find the return period as 1 by inverse of that. So inverse of this column, it will be 11. This will be 5.5, 3.67. This will be 2.75, 2.20, 1.83, 1.57, 1.38, 1.22, and 1.10. So we, for each of the discharge values, we have our corresponding exceedance probability, and also we have a corresponding return period. And the question we have been asked to find the for the blood magnitude for the return period 5, 10, and 20. So we have the values with us. We can interpolate and find the corresponding values. So now we from the table we can just do linear interpolation. We will assume linear variability and we can do linear interpolation and find those values. So we can start with for t equal to 5 years. So 5 years if we are going, then t1 is equal. So we can say it is lies between 5 t1 and t2, right? T2 will be 3.67. It lies between 5.5 and 3.67. Right. 5 will lie between these two. So corresponding to Q1, our T1, our Q1 is 5020, and corresponding to T2, our Q2 will be 4700. So now we need to do the linear interpolation. So Q will be equal to the Q1 plus the formula T by T1, T minus T by T1, T minus T1 by T2 minus T1 into Q2 minus this simple linear interpolation formula. So if you substitute that, Q1 is 5020, T is for 5 we need to find, T1 is 5.5, T2 T2 is 3.67 minus 5.5. So 8.5, and in Q2 minus Q1 is 4700 minus 5020. Okay, so if you solve that, we'll be getting it as 5020 minus 87, that is equal to 4933 cubic. So that is the blood magnitude corresponding to a return period of 5 years. So similarly, we can do it for t equal to 10 years. So 10 year will lie between T1, that is 11, which has a Q1 of 6100, and T2, that is 5.5, which has a Q2 of 5020. Directly we can substitute, we have already written the equation. So it will be 6100 plus 10 minus 11 by 5.5 minus 11 into 5020 minus 6100. So Q will be coming out to be 6100 minus 196. So that is 5904 cubic. Okay, so one more third part is T is equal to 25 years. So here our T was only till 11 years. So here we have something we need to do is extrapolation. So here the difference is we are going to do an extrapolation, not interpolation, extrapolation. So here Q will be 6100 plus 10 minus 11 by 5.5 minus 11. That is the limit, right? 5020 minus 6100, right? So this will be 6100 minus 196, that is equal to 5904 cubic. So it will be not minus, sorry, this will be, so, uh, sorry, this will be, this part was wrong. We're doing extrapolation, yes. 25 minus 11 divided by 5.5 minus 11 and 5020 minus 6100. Right. So this will be coming around plus 2749 will be around 8849 cubic. We were extrapolating that, right? So finally, we have one more part, that is we need to find the flood magnitude and the return for the corresponding 4000. So 4000 cubic, so it is the opposite, but we have what we need to do is interpolation only. So return period T for Q is equal to 4000 cubic. That is also straightforward, right? So Q1, Q 4000 will lie between 4000 and Q2 we have 4200, 4200 we have, and also 3780 we are having. Plus one return periods are 2.2 and T2 is 1.83. The return period we can find using this formula, interpolation formula, T1 plus Q minus Q1, Q2 minus Q1, T2 minus T1. Just substitute it, 2.2 plus 4000 minus 4200, 3780 minus 4200, 1.83 minus 2.2. So this will be 2.2 minus 0.176. It will be 2.02 years. So that is the return period corresponding to 4000 cubic, right? So this is how we solve using floating point method. So if we are not trying to fit with any of the distribution, we can do such similar methods. There are different formulas to find the external probability based on the rank and the number of observations. Using that, we can directly find and do interpolation to get the estimate of the return period and also the exceedance flood values. Okay, so I'm stopping the stochastic hydrology concepts here. So if you have any doubt in this particular section, you can contact me. So my name is KG and my email ID is KHILJNANADEBAN at gmail.com. I'm closing this section. Thanks for watching.